for our fourth talk of today. We have Daniel Duarte from Universidad, Autónoma, Zacatecas, and CONACyT, who is going to talk about the model of high order Kähler differentials and the Hasse Schmidt algebra. Okay, thank you, Daniel. Go ahead.
Okay, well, hello everybody. Thank you all for being here, and of course, thanks to Jack and Luis for their kind invitation to participate in this session. This talk is about a joint work with Paul Barajas from the University of Zacatecas, and this project started as an attempt to generalize to the module of high-order Kähler differentials, okay, some recent results by Tommaso de Fernex and Roy Docampo regarding the module of classical Kähler differentials and the Hasse Schmidt algebra. Okay, so I'm going to start by recalling this notion. Okay, recall that for A and B K algebras, a Hasse Schmidt derivation of order n, a natural number from A to B, is a sequence of linear maps, okay, from A to B, satisfying this Leibniz formula. Okay, this is a Hasse Schmidt derivation. Now, there is a dual object, okay, and which is called the Hasse Schmidt algebra, okay, and can be described as follows. Okay, there exists Hasse Schmidt this algebra, which we denote like this, okay, and a Hasse Schmidt derivation, which we call universal Hasse Schmidt derivation, okay, from A to this algebra, such that any Hasse Schmidt derivation from A to B factors through this algebra. Okay, so dual in this sense, exactly like happens with classical derivations and the module of Kähler differentials. Okay, now with this object, okay, and the module of Kähler differentials, the Fernex Docampo provided the following formula. Okay, they proved, okay, recently that the module of Kähler differentials, okay, of the Hasse Schmidt algebra can be decomposed using the module of Kähler differentials of the original ring tensored with this quotient, these jets, okay, of order n over this algebra. Okay, now, of course, this is a purely algebraic statement, okay, but it has an amazing amount of geometric applications. Okay, for instance, they used this formula to deduce a bunch of theorems regarding the structure of arc spaces and jet schemes. Okay, in a subsequent paper later on, they studied the problem of projectivizing induced morphisms on jet schemes. Okay, and again, this formula plays a key role. Okay, this is the application and we are interested in. Okay, now to discuss this application, I need to recall the general definition of blow-ups of coherent sheaves. Okay, so here we go. This is a construction that appears in the work of several people. Okay, all these people. And it goes like this, okay? Starting with X, a Noetherian integral scheme, and M, a coherent sheaf on X, the theorem says that there exists a projective birational morphism, okay, from some scheme to X with this property, okay? The pullback of this sheaf, mod the torsion, is flat over this scheme, and it is universal with respect to the previous property. Okay, and this is what they all call the blow up of X at M. Okay, for example, if you make M to be the module of Kähler differentials, okay, of X, okay, if X is an algebraic variety, okay, you take the module of Kähler differentials, then this blow up is nothing but the classical Nash blow up, okay, of X. Okay, if you take M to be the module of high order Kähler differentials, I will define this in a minute. Okay, if you take this one, okay, then this blow up is what is known as the higher Nash blow up. Okay, this is a higher order version of the Nash blow up. This equality is actually a theorem, okay, proved by Takeshi Koyasuda. Okay, now, so with this notion, we can discuss this application given by the Fernandez-Ocampo, okay, related to this formula. Okay, and the thing is how to compare, the question is how to compare these blow-ups with jet schemes. Okay, I'm going to draw a diagram. Okay, we start right here. Okay, we starting with X. Okay, we consider this blow-up at this module. Okay, and then we consider the induced morphism on jet schemes. Okay, for some n. It is known that properties, okay, of the original morphism are not necessarily true for the induced morphism. For example, this one is projective, this one not necessarily. Okay, so the Fernandez-Ocampo considers the question of how to projectivize this morphism. Okay, find another morphism which you know is projective that factors this one. Okay. Now, to answer this question, we reduce everything to the affine case, okay? And so X is the spec of a ring, and it is known that the jet scheme is the spec precisely of the Hasse Schmidt algebra, okay? Now, we have associated a module here, okay, the original module, and then they consider this other module, okay? They give a very special Hasse Schmidt algebra structure, okay, as module, sorry, to this module, okay? And then they prove that in order to projectivize this map, what you have to do is to blow up this module, okay? So the theorem is the following, okay? They prove that if you take the blow up of this new module, then there exists a map here, okay, making this diagram commutative, okay? So they answer this question in full generality, okay? Now, in the particular case of M being the module of Kähler differentials, because of the formula, they can prove, they deduce, okay, that this blow up, the blow up of this weird module is actually the Nash blow up of the jet scheme, okay? So for omega-1, the answer they give is quite satisfactory, okay? They combine this blue general result with the formula, and then they obtain this isomorphism, okay? And now, I presented you before a higher order version of Nash blowups. So I would like to know whether for these high order Kähler differentials, we have also an equality here, an isomorphism, okay? But following the Fernandez-Ocampo, the question is whether there is a higher order formula, okay? So now let me go to the question, but first, okay, let me recall this, this definition, okay? Omega m, okay, denotes this quotient, I over I to the n plus 1, where I is the kernel of the multiplication map, okay? So for instance, if m equal 1, this is just the usual classical Kähler differentials, okay? And so the Fernandez-Ocampo provided this formula, okay? And we would like to know, because of this geometric application, this geometric motivation, we would like to know whether there is a higher order formula, okay? Now, I don't want to create any suspense here, okay? The truth is that this question turned out to be spectacularly false, okay? Not only we found a counterexample, okay, we can essentially prove or show that any reasonable example is a counterexample, okay? So this is the first, sorry, bad news, okay? If you consider any finitely generated K algebra such that the Hasse Schmidt algebra is a domain, for instance, consider A to be the polynomial ring, okay? Then the expected formula, the desired formula, holds only for m equal 1, okay? So there is no way to have this isomorphism, this higher order formula, okay? Now, how do you prove this? Well, first, you need to know that both modules are well behaved with respect to localization, okay? Once you know this, then it's just a matter of localizing, okay, at non-singular points, and on the left side, you obtain a free module of this rank, okay, and on the other side, a free module of this rank. A straightforward combinatorial argument shows that these two numbers are equal only for m equal 1. Okay, so forget it. We don't have a higher order formula because the generic rank increases differently. Okay, this is the reason. Okay, so now we go back to the question. Okay, which was the diagram. Okay, if M is this module of high order color differentials, we want to know whether this diagram, okay, this blue blow up turns into this Nash blow up. For M equal 1, this follows by the Fernandez-Docampo formula. For M greater than 1, there is no formula. Okay, so we don't know, okay, whether these two are isomorphic. Okay, the question is still there. So the best we have regarding the problem of projectivizing this map is the Fernandez-Docampo. Okay, the Fernandez-Docampo's result. Thing is that, what is this blow up? I mean, what it does to the variety. For instance, the Nash blow ups, they have a very, very nice geometric description. Okay, they replace singular points by limits of tangent spaces. Okay, so very nice geometric description. What about this one? Okay, what can we say about the blow up of this module? Okay, so in the rest of the talk, I'm going to show you that we don't know if they are equal, but at least they share a basic property of Nash blow ups. Okay, so this is like the second part of the talk. Okay, and here we go. To do this, we need to see how to compute these blow ups in the affine case. Okay. Is there a question, Luis, or should I continue?
Yes, there is a comment from Lung Oeding. Says, most tensors are not pure. It's a tensor product of elements from each factor. So we want to think about sums of pure tensors. Perhaps there is a reasonable conjecture for layer M as not for a pure tensor product, but a sum of such.
I have no idea. I have no idea. I don't know. We never tried this. We never thought about this. No, I don't know. I don't know. Instead of taking just this tensor, to think of some of these tensors, I wouldn't know. I don't know. I don't know. We haven't tried. But
I was just reminded of the the very first formula that you put on your first slide, that the derivation splits up as a sum of a bunch of derivations on the individual parts. So you could imagine that the modules that you're looking at could not have the pure tensor product property, but maybe the thing you're hoping to be isomorphic to is a sum of a bunch of modules that are tensor products themselves.
Okay, thank you. We never thought about this, but that's a great idea. Okay, thank you.
Yeah.
Okay, thank you. Okay, well, so let me continue. I was discussing how to compute this, the blow up of coherent shifts in the affine case. Okay, so in this context, we have a Noetherian domain and M a finitely generated A module. Okay, now we need the following ingredients. Okay, first we need a presentation. So we're back to the general case. Okay, so we need a presentation of this module. Okay, given by some matrix. Okay, with these numbers here. Then we need to know the generic rank, which is the dimension of this tensor. Okay, f of A is the field of fractions of A. And with these numbers from the matrix L, we have to take, okay, a submatrix formed by this amount of columns, okay, and having maximal rank. Okay. Okay, so in other words, we have this matrix, and we're going to take some columns in there, okay, form a new matrix, and this new matrix must have maximal rank. Okay, with these ingredients, Orlando Villamayor proved that by taking the ideal generated by the maximal minors of L prime, okay, then the blow up of this module, okay, or the corresponding coherent shift, is the blow up of this ideal. Okay, so this is going to be our main tool to compute these blow ups. Okay, so we want to find these three ingredients for the specific module that we are studying. Okay, the one that the Fernandez-Docampo introduced. Okay, in the particular case of omega m. Okay, so first, a presentation, okay? Recently, together with Paul Barajas and independently, Olger Brenner, Jack Jeffries, and Luis Núñez-Betancourt, okay, we proved that for finitely generated algebras, okay, there is this presentation of omega m, okay? So it's very similar to what happens to the module of Kähler differentials, but here we must take, okay, higher order derivatives, okay? So a huge matrix with a lot of derivatives, okay, arranged in some order, okay? So we have a presentation, explicit presentation, okay? So taking this as our starting point, okay, we tensored with these jets, and then this sequence becomes this one, okay? Here you have to do, you know, some commutative algebra, chase some diagrams, play with all the module structures appearing in this context, and then you can describe explicitly a matrix here, okay? And then you obtain a nice corollary, okay? Because if you do this for m equal 1, it turns out that this matrix is actually the Jacobian matrix of the Hasse Schmidt algebra. So as a corollary, we recover the formula given by the Fernex Docampo in the case of finitely generated algebras. Okay, so this is like a nice corollary. Okay, so we have a presentation, okay, given by some matrix, explicit presentation. The generic rank. Okay, so recall the ingredients: presentation, generic rank, and the submatrix. Now, to discuss these two ingredients, let me explain what we did in an example. Okay, consider the cusp. Okay, f is this polynomial. Okay, m is 2 and equal 1. Okay, the smallest possible numbers. Okay, and then, okay, the first theorem, okay, says that we have this presentation with this matrix. Okay, there appear some first partial derivatives, derivatives of order 1, etc. Okay, now we go to this one. Okay, to the tensor. Okay, and obtain the following matrix. Okay, so of course it's going to be a bigger matrix. Okay, so we have this sequence with this matrix. Here there are some details to explain, but right now I just want to emphasize that this matrix is written in form echelon, in row echelon form. Okay, okay, so in particular it has maximal rank. Okay, so there is no kernel here. Okay, so we obtain this exact sequence. Once you have this, to compute the generic rank is straightforward. Okay, just tensor, you know, sum, subtract, etc. You have the generic rank. And finally, because of the numbers appearing, okay, all the numbers appearing in this context, it turns out that the submatrix required by Orlando Villamayor is actually the matrix itself. Okay, so we don't have to look for a submatrix; it's the matrix itself. Okay. Well, everything I just said holds in general for hypersurfaces. Okay, so let me state this. Okay, for hypersurfaces, and assuming that X and the jet scheme of order n for some n are irreducible, then we can obtain a similar free resolution. Okay, so we have this projective dimension is less or equal than 1, and again, because of the numbers involved appearing in these computations, Villamayor submatrix is actually the matrix itself. Okay, so this, okay, all these results are our main tool. Okay, our main tool. Okay, to study this blow up. Okay, I'm almost out of time. So very briefly, the property that I want to study, to compare, okay, from this blow up to Nash blow ups is something called Nobile's theorem. Okay, using the previous method, for instance, okay, we know that the Nash blow up, okay, of a hypersurface is just the blow up of the Jacobian ideal, okay, the partial derivatives. But then in characteristic 2, this is a principal ideal, okay? But to blow up a principal ideal is an isomorphism. So this is terrible. You start with a very simple curve singularity, do the Nash blow up in characteristic 2, and you obtain the exact same curve. In characteristic 0, this cannot happen. This is Nobile's theorem, okay? If it happens that the Nash blow up is an isomorphism, it is because the variety was already non-singular, okay? This is a basic property of Nash blowups. Of course, in characteristic P, this is false, okay? You have a singular variety and still you have an isomorphism. In a recent paper, in a recent work together with Núñez-Betancourt, we proved that by adding normality, okay, this condition to the variety, then we can recover the Nobiles theorem, okay? If you have an isomorphism, then X is non-singular, okay? So normal is the key assumption. Well, we can prove using the previous description, the previous tools, that this property also holds for the blow-up of this module, okay, in the case of hypersurface, okay? So this is the final statement, the final theorem, okay, for a hypersurface, assuming that the jet scheme is irreducible and normal, again normal. Notice that this is a free of characteristic statement, okay? So we have the same statement. Blow up of this jet scheme at this module, an isomorphism implies that this one is non-singular, okay? So since I'm running out of time, my time is over, I think I should stop here. So thanks for your attention.
Thank you, Daniel. Are there questions for him?
Okay. Maybe I would like to say a little more about this suggestion given by somebody. I'm sorry, I don't know the name. Look, there is a closely related notion called flag higher Nash blowups, flag Nash blowups, and they consider not only omega m, but sums from, maybe this is not very rigorous, but something like sum of these higher order modules from 1 to m, okay? So maybe for these blowups, what you are suggesting might work, okay? But this is called flag higher Nash blowups. Maybe.
Yeah, I was just thinking, like, if you take the tensor product of two modules and then you try to take a symmetric power of that, what you get afterwards is not just a tensor product of two modules, the sum of a bunch of them. The Cauchy formula gives you all of them by partitions. And so you could imagine something similar could happen with these kinds of modules where, you know, you're taking a higher order version of the thing you had before, and in order 1, it's just the pure tensor product of modules, but in order 2 and higher, then it's something not irreducible or not just a tensor product. So yeah, maybe the flag is the right thing, right? I mean, sum of order 1, order 2, and so on.
Okay. Yeah. Thank you. But that's interesting. Yeah.
Nice
Are there
talk,
more questions?
by the way. It's hard to give feedback during Zoom, but yeah, nice talk.
Thank you.
Are there more questions for Daniel? Okay, well, I have one in the meantime. So here you're taking differentials, not higher caliber differentials. I guess you take principal parts is the same, no? There's no problem.
I don't know, Luis. I don't know, because you know, let me go back to the beginning. Okay, it usually works, you know, because the difference between the principal parts and this omega, sorry, where is it? The principal parts and this one is just a free factor. But the thing is that when you go to our proof, the numbers appearing, okay, here you just have to remove this -1, right? Because of the ranks. But then this statement is not true. These two numbers, if you remove them once, these numbers are, I mean, even for m = 1, they are not equal. Okay, so I was actually planning, following your usual suggestion, to talk about principal parts instead of this omega m, but I got into this problem. If you remove this -1, this is not true. So together with Paul, we started discussing this, why, what is the difference? But this was like, I don't know, Friday afternoon, so we didn't continue. So I decided to do everything with omega m. But I don't know, there are some things to check. And it's the problem, we thought that the problem is related to what is the structure of Hasse Schmidt module of this tensor, because it's not the straightforward one. Okay, it's a particular one using the universal hash derivation. That's the reason, maybe.
Okay. And then second question, like in characteristic P, there is this notion of F flow up. So instead of these differentials, you take something like the P roots, or does it? Have you tried? Have you seen something there, or like something?
No, not really. I mean, in this direction, maybe there are some works by Yasuda where he considers these notions. He works directly with Frobenius morphism, and then he applies somehow he compares his blow-ups with this blow-up, and then he develops these notions. There he has also some sort of, I don't know, Nobile's theorem follows by Kuhn's theorems, but no, we haven't tried. But if you're interested, it is at Yasuda's work in positive characteristic where you should look at. Yeah.
Okay. Okay. Thank you. If there is a question, well, if not, we thank Daniel again